All right, thank you very much. Thanks to the organizers for organizing such a great conference. Thanks all of you for coming back after the break. And you had a choice, so thank you for making this choice. Yeah, so I'll talk about some recent work that I've been doing in the last couple years on some irrationality questions of Erdős. I guess I should also say that some of this is supported by the NSF, and I hope it continues to exist. Okay, so Erdős's name has come up quite often in the conference. Of course, he talked about many different kinds of problems in mathematics and was interested in many different kinds of things. And one of the topics he returned to again and again was the irrationality of various kinds of numbers. But he had a sort of idiosyncratic approach to it. He wasn't interested in maybe the central currents or themes in irrationality and transcendence. He has this nice quote from a collection of problems. He says, "We will discuss here only special series which do not connect up with the general theory at all, but which seem attractive to us, and where often clever special methods are needed, which usually are not available in general." Okay, so there's maybe a hint of self-deprecation here, but I think there is actually a connection with the general theory that I'll try and elucidate as we go along. Okay, so to begin, I want to go back to Joseph Fourier's 1815 proof that the number e is irrational. So this is probably the most famous irrationality proof after the square root of 2. It actually shows up in a calculus textbook. Standards have fallen since then, I suppose. So all of these proofs are always by contradiction. So you assume that e is actually rational. It's a quotient of two positive integers, say a and b. And the nice thing that we have about e is we can write it as this infinite series, the reciprocal of the sum of the reciprocals of the factorials. Okay, and then the thing that you always do is you take away some of the initial terms and do some rescaling, and you're trying to get something that you know is an integer. That's the thing that we try and do. So you have some parameter capital N, which is a positive integer, natural number, and you take away the first n plus 1 terms and then multiply through by n factorial. And because we're assuming e is rational, this quantity I've called capital A is now actually an integer. And you can rewrite it in a different way, and you see that it's a sum. So 1 over n plus 1 plus 1 over n plus 1 times n plus 2, and so on. And of course, these terms are all quite small. This whole thing is just bounded by 1 over capital N. So it's supposed to be a positive integer, but the terms in the series decrease so quickly that it can't possibly be a positive integer. As soon as capital N is 2 or something, then you're getting an integer strictly between 0 and 1. And of course, this thing does not exist. Okay, so this is quite a simple proof, but there are some themes here we can extract that we'll see several times moving forward. So here are some general principles of irrationality we might extract from the proof. So you have some number a given by an infinite series, and of course you expect generically it should be irrational. And if you assume for contradiction that it's rational, this will give rise to some sort of integrality or rigidity condition. And if the terms in the series, if they decrease very quickly, there aren't too many terms you'll have to consider. And then somehow you use your knowledge of the terms of the series to show that there's too much flexibility for this rigidity condition to always be satisfied. Okay, so this is somehow very vague, but these are some general principles that we're going to see. All right, so let's look at a more concrete example. So there's a conjecture going back to Erdős and Katz in the early 1950s. They define this function sigma k of n, which is the sum of the kth powers of the divisors of an integer. And then you stick these all together over some factorials and you get some number. Okay, so I'll call it alpha k. And they conjecture that this is irrational for every positive integer k. Because why not? All right, so This gives you an infinite series of problems, one for every positive integer k. Alpha 1 and alpha 2 are quite easily shown to be irrational. So if you get bored during the rest of my talk, feel free to work on these exercises instead. Alpha 3, so the next case, was also shown to be irrational by some sieve theoretic arguments, independently by two different groups, Schlager-Pupta and Friedlander, Lucke, and Stoische. This was around the mid-2000s. And it's actually known that all of these numbers are irrational, assuming some strong number theoretic conjectures. Okay. But unconditionally, we only knew something about the first three. So a couple years ago, I showed that actually the fourth number is also irrational. Surely it's not a coincidence that the number 42 is showing up here, some sort of key to the mystery of the universe, as you might be aware. So this argument also relies on sieve theory, but somehow the arguments are much more complicated than the previous cases. And it really seems like maybe we need some substantially new ideas to go further. The case k equals 4 seems to push things, the sieve theory ideas, to their limits. Okay, so let's talk a little bit about the ideas in this proof, and we're going to return to some of these themes that we saw earlier in Fourier's proof. So again, assume that it's rational, so we have some a over b. And then we do the same thing, so we're going to take away some of the initial terms, and then we're going to do some rescaling. Okay, so now we're going to use a prime p for reasons that we'll see soon. So I have this number capital A, and when I take away the initial terms and I do this rescaling, this is going to be an integer. Again, we're crucially using the rationality here. If p is large enough, then b will divide p minus 1 factorial. Okay. And you know that this sigma 4 of n, it can't be too large. It's like a constant times n to the fourth at most. So if you look at the size of the terms of the series, only a few of the terms will actually matter, right? If you start writing out what this capital A is equal to, the n equals p term and the p plus 1 term and so on, only the first 4 of them are actually going to matter, and the rest of them are very small. So these 4 terms here, their sum has to be very close to an integer. Okay, not exactly an integer, but very close to an integer. And this is our rigid integrality condition. And the way that I like to think about this is that there's some sort of conspiracy that these numbers have all entered into together. So the conspiracy that you're trying to rule out is that the prime factors of p, p plus 1, p plus 2, and p plus 3 are all conspiring together to make the sum of these terms always very close to an integer. Somehow this is the thing that you have to show cannot happen. Okay, so a bit of notation. You have this double bars around theta, so it's the distance from theta to the closest integer. So just rewriting the conclusion from the previous slide that the sum of these 4 terms is quite close to an integer. And now what you're trying to do is pick off individual members of the conspiracy, okay? So since p is a prime, the first term already is quite close to an integer. Sigma 4 of p over p is just p cubed plus 1 over p. And we're going to try and impose other conditions and control as much as we can this potential conspiracy. So p plus 3, of course, is going to be even if p is a large prime. So it'll have a factor of 2, but let's insist that it doesn't have any other small factors. You can do this with some sieve theory. And also, we're going to require p plus 2 to have a stronger condition on its prime factors, say no primes less than about x to the quarter. Okay, so there's some quantitative analysis you have to do here, but if you impose these kinds of conditions, you can show that this bottom condition holds. So there's something involving the prime factors of p plus 1, and then you get a 1/16 coming out from the p plus 3 over 2. And this has to still be pretty close to an integer, okay, 1 over log x to some decently large power. So we've arrested most of the members of the conspiracy, but one of them is still somehow at large, and you have to show that for most primes p, with these various prime factor conditions on the shifted prime factors, it's not possible that somehow the prime factors of p plus 1 always conspire to be very close to an integer. Okay. And the thing that we use is that generically, shifted primes have prime factors very similar to just ordinary integers. Okay, so like p plus 1 will have a prime factor of size x to the epsilon, at least on average. And then you can use some multiplicativity to induce separation, and you get two variables where before you had one. So maybe I have an L and a Q now. So Q is a prime of some small size, and L is some other integer. And you can use some positivity and some Fourier analysis, and what it comes down to is bounding some exponential sums. So the key point is that we have some separation now between L and Q, and we can make them somehow independent of each other. And as Q or N runs over some little interval, the fractional parts are going to be changing, and they can't concentrate very close to an integer. Okay, so you can end up finding large primes that satisfy all these different conditions, but this fractional part condition fails. So you end up getting some kind of contradiction here. Okay. So this problem, with these alpha k's and the sigma k's doesn't seem entirely motivated, perhaps. I want to make an argument that there is something in the main line related to this. So we have this idea of Siegel E functions, which were introduced by Siegel in his very influential 1929 paper. So these are some sort of power series that you make. So you have a sequence of coefficients a sub n, like algebraic integers or maybe algebraic numbers with some constrained denominators. And you can get this function f of z, and it turns out to be an entire function. You don't let the an's grow too quickly. And then there's a very satisfactory theory, actually, as long as f of z has some suitable, what I'll call differential structure. If it satisfies like some reasonable differential equations, like the canonical example would be something like e to the z, and it's the derivative of e to the z is just itself again, which is some very nice differential structure. And as long as you have some sort of differential structure on your e function, we actually have some pretty good transcendence results. Like almost always, if I plug in an algebraic number into an e function, it's going to be transcendental, actually. You might think about trying to make an e function with these sigma k arithmetic functions. You don't get any nice differential structure at all, but it's certainly very natural to conjecture that if I plug in any kind of non-zero algebraic number, I should get something transcendental. Okay? Of course, we're very far from proving anything like this. And you might hope that maybe some arithmetic structure could overcome a lack of differential structure. So I think there is a tie-in with some more general themes, but we're very far from being able to do anything like this. Okay. Let's talk about something a little bit different now. So an early irrationality result of Erdős goes to the late 1940s, and it has to do with the divisor function. So I'll let tau of n be the divisor function, and we're going to form again an infinite series with the divisor function, but now not with factorials, but just with a geometric series, 1 over 2 to the n. Okay? And this number, I'll call it s. This is also irrational. Okay, so let's go very briefly over the proof. And again, we're going to see some of the themes that we've seen before. So you assume that s is actually rational, and then you take away the first few terms, and then you do some rescaling, and you get some integer. Okay, this capital A has to be an integer. And then what we're going to do is again try and induce some sort of conspiracy that we can rule out. Okay, so we split this sum over k into 3 different parts. So maybe think small and medium and large or something like this. And there's some parameters here, capital K and capital L. Don't worry too much about those. And the idea is that we're going to induce some very weird particular behavior for the divisor function, but also try and take advantage of generic behavior of the divisor function. Okay, so this capital A is an integer, and for the small terms, we're just going to make all of the tau of n plus k's over 2 to the k's. We're also going to make all of those into integers. How could you do this? Well, I want the divisor function n plus k to be divisible by 2 to the k. So I just need tau of n, or I just need n plus k to be divisible by at least k different primes, right? Tau of p is going to be equal to 2, and it has some multiplicativity, right? So if it has at least k different prime factors, then it's divisible by 2 to the k. So that's how we handle the small terms. You sort of make all of them an integer, and then you can get rid of them. And now for the rest of the terms, the medium size and the large size, you can actually show that those will be small, too small in order for this, the combination of everything to be an integer. So we make the small terms have some very atypical behavior. The divisor function will be very large on these terms. But then there's some sort of independence where even though some weird stuff is happening at the beginning, generically the divisor function will still be kind of small later on. Okay, so the upshot is that the sum of the k's up to this capital K, it's an integer, but after that the sum is just too small to get to somehow the next integer. Okay. One thing to notice about this conspiracy here is that there's many more members in the conspiracy, right? So in the previous example with the sigma k's, there was like 4 different people we had to round up in the crew, right? Danny Ocean getting his people to rob the bank. There was only 4 of them, but now there's a lot of them, right? Log x to the 1/10 or something. Okay. So you can play this game with other kinds of arithmetic functions, like omega n or phi of n or sigma of n, so the number of distinct prime factors, or the Euler-Totient, or just the sum of divisors, so sigma 1. And Erdős conjectured in that same paper that all of these were irrational. So you can try and follow the same simple-minded ideas that we've been following, like we did with the divisor function. One problem you run into immediately is that phi of n and sigma of n are actually quite large, right? Like of size n. And the divisor function is much smaller than that. So there are many, many members in this conspiracy. You have to try and arrest all of them and deal with them. But there's just a lot to handle. Omega of n is much smaller on average, right? It's like log n on average, or at most log n or something. So there are fewer terms to control, but somehow I'm going to need like global information now about the prime factors of an n. The divisor function is multiplicative, and you somehow only need like local information. Like only partial information will let me control some terms. But with omega of n, it's literally like, okay, well, how many total prime factors do I have? So there's somehow more information that you need, and you need information about the prime factors of many consecutive numbers. So this seems hard. There actually is one case in which this has been solved. So with the sigma of n arithmetic function, this was solved in work of Nestorenko, some very nice deep work. I have no reason to think Nestorenko was motivated by this particular conjecture of Erdős. He almost certainly wasn't. But he does a lot of amazing things in this paper. And something he shows is that if you plug in any algebraic number, between 0 and 1 in absolute value, then actually this sum is going to be transcendental. Okay, so taking gamma equal to 1/2 will recover Erdős's conjecture. But the proof method of Nestorenko is somehow not this simple-minded thing that we've been doing, but it's actually quite deep and much more typical of what's going on in transcendence and irrationality proofs. Okay, so you first use the happy coincidence that sigma of n is actually the coefficient of some weight 2 quasi-modular Eisenstein series. And then again, you have this differential structure that comes into play. So if you look at the ring of Eisenstein series, so the weight 2, the weight 4, and the weight 6 Eisenstein series, this actually happens to be closed under the action of some differential operator. This goes back to work of Ramanujan, actually. And then you do the typical thing. You have to construct some auxiliary function, auxiliary polynomial, and make it vanish to really high order somewhere. You have to show that something is not 0. Okay, if you know this game, you know how it goes, and if you don't, you won't believe that any of this could possibly work, but it does. And then you need some very deep estimate that ends up coming from commutative algebra. Okay, so in one particular case, these hard conjectures of Erdős have actually been answered by very different kinds of methods. But it relied on this sort of miracle that sigma of n is actually related to some very structured modular form object, which there's no reason this should happen in general. There is one other case that I can sort of say something about. So the case with omega of n, the number of distinct prime factors of n. assuming some suitable version of the prime k-tuples conjecture. Okay. I have no idea how to do this unconditionally, but if you assume some version of the prime k-tuples conjecture, then you can show that these numbers beta t are actually irrational for every positive integer t at least 2. Okay, let me just say something briefly about the prime k-tuples conjecture. So you have some kind of linear forms. So you have some coefficients ai and bi. And you need, if you have a collection of linear forms, you want them to all be prime infinitely often when I plug in some n. But there's a notion of admissibility that you need. The way to think about admissibility is like there's no obvious reason that they can't all be prime infinitely often. So if I have the linear form n and n plus 1, this clearly fails to be prime infinitely often because there's some parity obstruction. N and n plus 1 have opposite parity, so one of them is always even, so this can't possibly always take prime values. So you do some sort of local analysis, and if your set of linear forms doesn't have any obvious reason why they can't all be prime infinitely often, then we just conjecture that they should be able to be prime infinitely often. So somehow like this is saying the only conspiracy among the primes is somehow like the obvious conspiracy, that primes don't have any small prime factors. And the version of the prime k-tuples conjecture that we need is actually one that allows for some kind of uniformity, where like the number of linear forms can grow and the size of the coefficients can grow and stuff like this. Of course, we're very far from proving anything like this, but these conjectures are certainly believable. Okay, so how do we approach something like this? Again, we're singing the same song, just in different keys. So you always do the same thing. You take away some of the initial terms, and you do some rescaling, and you try and get something being an integer. Okay, so this capital A is now an integer, if you assume that the beta is rational. And then we're going to do the similar thing that we did with Erdős's divisor function result. We're going to split up our sum into small and medium and large and try and do different things in these different regimes. Okay, so again, you have some capital K and some capital L. Doesn't matter too much what's going on here. And we need to find some good cutoff n, which is going to show that actually this capital A is not an integer. We want to refute the conspiracy. Okay, so we're going to choose some capital N that's going to be divisible by all of the little k's. We'll see soon where this comes up. And then you split the sum into 3 parts, and the contribution of the largest part is just trivially small by some trivial bounds. Okay, so we have the small and medium ones that we have to deal with. So you write the sum over k in this way. And the thing that we notice is that there's a sort of self-similarity. I have n plus k, and if n is divisible by k, I can pull out a factor of k. And the sum separates like this, using the fact that omega is additive. So you have a sum of omega k, and then a sum of omega n over k plus 1. And the sum of omega k over t to the k, this looks like the initial segment of the thing that we started with. Okay, so if you add in the rest of the terms, you somehow get back to what you started with, and then you have this other thing going on with the omega n over k plus 1. And here this is where we say, well, this seems really hard, but if we use the prime k-tuples conjecture, we can just force all of these numbers to be prime. Okay, this doesn't look exactly like a set of linear forms, but you can make it look like this. So the prime k-tuples conjecture will let us find some large n where all of the n over k plus 1s are going to be prime for the k's up to this parameter capital K. And then you do some more analysis. You extend the sum to infinity, right? So if omega of n over k plus 1 is just 1 for all of those k's up to capital K, then this is just like the first part of a geometric series, just 1 over t to the k. And then I just extend the sum to infinity. And you see that the sum over k is this a plus b over t minus 1. Okay, so the whole sum over k is supposed to be very close to an integer, and the initial part actually has this fairly explicit form, a plus b over t minus 1, plus some small error. All right, and then you have the medium-sized terms, and we're going to do the exact same kind of thing that we did with the divisor function. So we impose some like very strong, kind of very weird conditions at the beginning. Everybody is prime, right? This sort of thing doesn't happen. But then for the medium-sized terms, you're going to rely on this generic behavior again. And there's some sort of independence where I can have something very rare going on, but then independently something typical is happening later. And typically, the omega function is not too big. Okay, it's normally distributed with mean and variance like log x. So certainly, very often it should be like bounded by log x squared, say. So we want all of the medium-sized terms to not be too big. And a small wrinkle that we need here is also that, say, the first of these terms, so after we deal with all the terms up to capital K, I want the next one, so the term n plus capital K plus 1, to not be too small. Okay? And this is also a completely generic thing to be happening because, again, you have this normal distribution, sort of at scale log x. And then what you want to show is that the medium-sized terms, they're very small. The total contribution is very small. But they're also not too small because we have the lower bound on this first term. You need this lower bound because you have some error terms floating around, and you want this term to somehow be big enough that the error terms are not going to overwhelm things. And again, what you end up showing is that there's some integer strictly between 0 and 1, which, of course, cannot happen. Okay, so there's some very complicated ideas going on here, but the themes keep repeating, right? You try and round up all the members of the conspiracy, and you have to control many different things. And sometimes you want very atypical behavior, and sometimes you want typical behavior. So this is an example of this flexibility I was talking about at the very beginning. All right, let me just say a little bit more about how you can actually choose this capital N. So there's a couple different choices we want here, right? So we want that n over k plus 1 is prime for many of these different k's, and also that capital N plus capital K plus 1 has sufficiently many prime factors. And you want to do some sort of counting argument to say that there's many choices of this capital N that you can make. So by the prime k-tuples conjecture, the number of n's with all these n over k plus 1s being prime is something like x times log x to the minus capital K. There's also some singular series here, so we're going to not really worry about this. And there, again, there's also the condition like n has to be divisible by all of these little k's up to capital K. So it's not exactly like this, but close enough. And then you just do some inclusion-exclusion. You say, OK, well, how many n's are there where all of the n over k plus 1s are prime, and this other number has too few prime factors, less than 1/10 log x prime factors. And it turns out that you can handle this with some sort of sieve theory argument. Okay, it's not a totally straightforward argument. It turns out to be somewhat complicated. You need zero density estimates and this kind of thing. But you can do this. You win some extra log x factor coming from the fact that n plus k plus 1 has this atypical number of prime factors. It has too few prime factors somehow. And you can win something extra from this. OK. So this also ties in, these sorts of weird Erdős problems, with geometric series. This also ties in with something in like the more general theory of irrationality and transcendence. These are called Siegel G functions. So the Siegel E functions are somehow supposed to generalize exponential functions. And the Siegel G functions somehow generalize geometric series. So a G function, you have some sequence of coefficients again, say algebraic integers. And you don't want them to grow too quickly. Say they're bounded, they only grow exponentially, some constant c to the n. So this power series f of z will have a radius of convergence, like a non-trivial radius of convergence, a convergence on some disk. And you can already see that maybe it's going to be harder to do things here because with e functions you had an entire function. And entire functions are somehow really nice and wonderful. But these more limited power series, they're only going to converge on some small disk, maybe. Okay, so there's not as much room to play with. Again, if your g function has some suitable differential structure, you can actually say something. There are some irrationality results, Bombieri and the Chudnovsky brothers and other people, Fritz Beukers. There are some irrationality results known. Currently, we don't really have any way to get transcendence results in the theory of g functions. Which is quite, at least via Siegel's sort of original envisioned approach. Of course, there are transcendence results, like the log function, log of 1 minus z or whatever, is also a g function. But somehow, these transcendence results are secretly coming from the theory of e functions, and you're like transporting them somehow to the theory of g functions. Okay, so in general, there's no reason to suspect any kind of differential structure for like an arithmetic function you just pluck out of the air. And again, you might ask, is there any way for this arithmetic structure to overcome this lack of differential structure? Okay, so in very limited situations, like with the divisor function or conditionally with the omega of n function, you can sometimes get some irrationality results. Okay, so maybe some other series to think about. Again, if you are bored in the last 10 minutes of the talk, or 5 minutes, you can think about some of these series. We didn't say anything about Erdős's conjecture with phi of n. This one seems very hard. I have no idea how to approach this. Also, these other ones, 1 over n factorial minus 1. So this is somehow similar to the series for e, but we have a minus 1 in the denominator, and this minus 1 just destroys everything. And then you could also imagine putting in like the nth prime or something with square-free numbers. I mean, you can sort of multiply conjectures endlessly. All of these seem to be quite difficult and point towards very tricky distributional information about these sequences. Okay, maybe very briefly I'll just talk about some very recent work of some other people of a different flavor on some of these Erdős irrationality questions. So Erdős made a conjecture that's this thing about you choose a rational number and a positive integer t at least 2. This rational number shouldn't be equal to minus any of the t of n's because we're going to sum up 1 over t of n plus q. So I never want the denominator to be 0. Erdős conjectured that this should always be irrational, and this was proved by Borwein a few years later. And you might wonder, okay, well, if I have the sequence t to the n, and I sort of sum that up against a rational number q, okay, Borwein shows that this is irrational. Well, what other kinds of sequences of integers can I plug in and still get something irrational? Okay, so there was a conjecture of Ken Stolarski that was later picked up by Erdős, and Erdős and Graham put it in their big book of conjectures. So the date is no later than 1980, but it could be much earlier. And the conjecture is that I just need any sequence of integers going to infinity where the sum of the reciprocal converges. Then you can find some positive integer t where this sum 1 over a n plus t is irrational. So this was the conjecture. And very recently, Kovács and Tao showed that actually this conjecture is just completely false, which is actually quite surprising. So they have some strictly increasing sequence of positive integers a sub n. And if I plug in any rational number that's not equal to the negative of one of these numbers in the sequence, the sum of 1 over a n plus t is going to converge to a rational number, which is quite surprising. What they use in the proof is somehow the fact that rational numbers are countable, so they're somehow easy to avoid, but they're also dense, so they're somehow hard to avoid. Okay, so there's lots of interesting questions in this area, and I encourage people to take a look at this. Thanks for your attention.